So we'll talk about more unsupervised learning today. Was it section 35, I think technically. And we're going to talk about clustering, which is a big one for unsupervised learning. Some reasons why we do clustering, well, unsupervised learning in general, but like clustering, the idea of it comes from the fact that things that are alike tend to be near each other. And we say near each other by some kind of distance metric. And that's kind of like the whole idea of how clustering can work. So I kind of like to think about it like you might have heard before. It's like, you tend to hang out with people who are similar to you just by nature of just like, you have similar tastes. So you just tend to be around each other. If you guys all like bowling, you'll tend to go all bowling to each other. So by looking at an individual and seeing what things are about them, you can kind of get an idea of what their friends are similar. It's like, it's not exact, right? It's obviously sometimes, things that are close together, maybe they're different and stuff like that. But that tends to be true. And it turns out to be true with most data, or at least that's the idea with clustering, is that data tends to be this way. So we'll have essentially multiple features, most of the stuff we'll see kind of examples will be mostly two-dimensional, but it obviously doesn't have to be. Usually clustering occurs in many, many high dimensions. And of course that kind of gives some issues with when you're using high dimensions is that it's hard to visualize. It can be computationally intensive. So kind of we talked about, I think yesterday, Sadr was there. We did PCA, and PCA allows you to basically reduce the dimensionality of your data set. In that way, you can first get more efficient. You can better efficiently run your algorithms. And also it can be useful, even if you don't use it to run your algorithms, it can be useful to help visualize. Since again, like I keep repeating this over and over again, as like the data scientist, as the human, you being able to visualize something is actually a huge plus because you are a great pattern recognition machine. Like humans just are really great at detecting patterns. So I always say, like, if you can, make a visualization. And then once you make that visualization, you can at least see if there's some underlying pattern that might be there, and then use the math in the code to guide you forward. But going the opposite direction, if you use just visualization, obviously that's no good. We need to formalize this kind of thing. But then also going just the opposite direction of using just the math, the code, it can lead you astray if you're not careful. So I think visualization is always a big part. Sometimes it's kind of ignored, but I think that's why you'll see me kind of draw things out and kind of show these parts. But anyways, that's kind of like the motivation of clustering. Basically, things that are very like are close together, and that's just in higher dimensional space. Okay, so we'll get right into this. So I'm going to start sharing my screen. And Zoom, why do you move my screens around everywhere? All right, so this should show KMeans. So you guys should be able to see that, all right? Cool, all right. So KMeans, so before we go into this, note that I'm going to talk about the algorithms as like, how they work, which I think is an important part. But in reality, when you implement this stuff, especially with like with scikit-learn, sklearn, when we import that package, you really don't need to know too much how the algorithm works. Like you can and this is where you'll see a lot of people actually just copy and paste code or just like write the thing in there. But I think there's a huge benefit understanding how these algorithms work, because it'll allow you to adjust the parameters and know when you're setting certain parameters up, what things to expect and what things you can adjust and maybe make more sense for your data set. So the first thing I want to show you is, I think the curriculum also links to this, but basically this is scikit-learn's website, right? Their documentation, and they talk about clustering here. And so clustering, the idea here is that you have a bunch of data. This is all two-dimensional data sets. And the idea here is you want to essentially identify which groups belong to each other. So at the very bottom here is like random data. Random data, for the most part, it's kind of tough to say what is, what a group is since it's random, which makes sense, right? Like if you saw this group and I asked you as a human, can you see this okay? It's not too small, right? Okay. But if you see this stuff right now, is that like you won't be able to say like what is the group that's within there as a human, right? And that kind of makes sense. It's random, it's just random, right? And you'll see on the columns right here are different algorithms that they can use to do clustering methods and stuff like this that are available in the sklearn. And you can see how they do different jobs, basically, of like how they classify. In this case, I think they say at most 3, or depending on the algorithm, they might be able to figure it out themselves. And you can see the different ones. Like, for example, all of these clustering algorithms do what you'd expect. They all cluster together. But you can see these differing kind of shapes. For example, these lines right here, these elongated, like lined groups. You can see that, like, probably as a human, you'd be like, oh yeah, it should probably look something like this right here, where it's like orange, blue, green. These black dots, by the way, just mean it's like noise. It says it's not part of the group. It just happens to be there. So certain algorithms allow you to do that. I think we'll talk about that today too, because I think that's an important thing that the curriculum doesn't talk about, but I just want to introduce like one aspect of that. But just know there's different kind of shapes. For example, this one is famous right here. These two crescent shapes or the kind of overlapping. Depending on the algorithm, some do really poorly on it and some do really great on it. So this is something that kind of consider what's your data set going to look like, and then say what kind of algorithm. And you can see no one algorithm, I mean, you can argue that maybe some of them make more sense, but no one algorithm is perfect all the way through. Like I'd probably say like agglomerate clustering looks pretty decent right here, but also know that sometimes you have to do the right parameters. So you can see there's some kind of bleed off right on these parts where it's green and orange. It didn't quite do a great job. And we'll talk about why this is versus dbScan. I personally like dbScan a lot because it identifies noise too, but there's other things that you can see like it didn't quite get this. So depending on your data set and depending on what your data should look like, this kind of determines what kind of algorithm. So that's kind of like one thing I want to apply with machine learning. Sometimes machine learning is kind of seen as you just throw a machine learning algorithm and it'll figure it out. And that's not true at all. You really have to understand what your data set's supposed to look like so you can apply the right algorithm. And that's why I always say like visualization is always a huge part. Okay, so cool. So it's kind of like a precursor of like what we're all going to see. So going to clustering, oops. All right. So the first clustering is something called K-means. And K-means is, I think, is a really powerful one. I always get it confused in my head when I say K-means and K-nearest neighbor, if you guys remember K-nearest neighbor. So I kind of almost imagine like K-means as like an unsupervised version of K-nearest neighbor, which is not quite right, but like in my mind at least it helps. But the K part represents that you get to choose what K is. And so this is actually a kind of nice thing in some ways, is that we get to decide how many clusters there are. So you can kind of go back to this data set over here, and you can see like, oh, if we know there's supposed to be 3 different groups, like it's pretty straightforward. It's like, oh, 3 different groups going through this. And I think I mentioned this to Assad yesterday when we're talking about unsupervised learning, is that sometimes if you don't, let's say certain algorithms allow you to just basically, you figure it out. You figure out how many groups there are. Sometimes the algorithm will divide things up in unintuitive ways. So one example I had was like an apple and an orange and say, all right, here's a bunch of pictures of apples and oranges and features about it. Unsupervised learning algorithm, figure it out. And ideally, you probably would thought, oh, oranges and apples would be completely separate groups. But it's possible that unsupervised learning says, oh, well, apples and oranges are different groups, but then also they're green apples, and that's a completely different group. And that might be something you didn't expect. Maybe you're like, well, I really want the apples, not just green apples separately. Or some other, depending on the situation, you might actually have where oranges and apples are more closely related, and it'll say, oh, this is one group, these red apples and oranges, and these green apples are a separate group, completely different from these. So these are things that unsupervised, you're not telling it what to look for. Basically, you say, if you figure it out. And so this is kind of like the danger, not the danger, but like something to always keep in mind. So it's kind of going back to K-means. You get to choose how many groups there are. You just basically first decide how many clusters you have. So you kind of have to have an idea, hopefully, of what you want. You can also basically, one way we do this is just literally do many different clusters. If we don't know how many clusters there are, we just say, all right, let's start off with like 5, go to 6, go to 8, go to 10, and so on. And we'll basically evaluate from there and say, all right, what's the best K in this case. But the first step is just determining how many clusters there are. And then we're going to initiate random centers. So I should actually, oh, do I not have my data set here? Oh, okay. I'm going to kind of, I thought I had my data set. Hold on, guys. I'm going to expand this out. Usually I had it all from you guys for a second. Ah, there it is. Ah, that's what threw me off. Nothing to see here. All right. So imagine you have a data set here. And let's say we take something like, something that's nice, like this guy over here. So you see there's a bunch of little data points. So what we'll do, we'll basically initiate random centers. So basically you get a center for each cluster. So if I say there's 2 clusters, K equals 2, I would have 2 different centers. And I just randomly put them somewhere, okay? And I randomly put them in somewhere and I say, okay, got these set. And obviously these centers are not gonna be probably associated with the actual data set itself. So what we're gonna do then is like, well, we wanna move those centers, and the idea is those centers represent those different clusters. So points that are near a center, that would be like cluster number 1. And then if you have another center with a bunch of data points around, that would be cluster number 2. That's what we kind of want to achieve here. And so what we do here, we initiate those centers, and then we're just going to repeat this process back and forth. We're going to assign and optimize. Basically, the first thing is say, all right, of all the points based on the center, which ones belong to that cluster? Okay, so we'll talk about this, and I'll show you guys a visual that's much better than me just talking out loud, but I'm just gonna give you guys the overall thing. Basically, you assign and say, all right, what points belong to each center based on distance, okay? And we can decide how that distance is made. And then say, all right, those are all the points, and then we're gonna optimize by moving the centers to minimize the total distance of those ones that we identified as being part of the group. So essentially what we do, we say, all right, here's our centers, okay, data points. All right, everyone over here, you are, group 1. Okay, everyone over here, you're group 2. Okay, let's move the center so you're more centered into the rest of the data set, and then you reassign. So sometimes you'll move your centers. In fact, most of the time you move your centers towards your data points, and you'll find that it will reassign new points. So like before these points were on group 1, but instead now it's part of group 2. So, and just we keep repeating that, usually until we basically don't have a major change or so many iterations. So we have like the most number of iterations we have. I think the curriculum says like until there's no new assignments, but that's not necessarily true. Sometimes we'll keep repeating it at least a minimum number of times just to make sure that it does work. So the best thing to do, I think this is a great visualization, by the way, and these are all on GitHub now, so you guys can access this. But this website right here has a great job of visualizing K-means clustering. So I'm just gonna go ahead and I'll show you, I'll choose the points. So it's just asking me what kind of data I have. So in this case, let's go ahead and do, let's just go example A. Let's see what this is. No, I don't like it. So I'll choose Gaussian mixture. Okay, this is good. So you can see, obviously they're like, they're obviously 3 groups here, but we're gonna randomly put them in. So let's say I put one group here. So that's my red group. I'll put my blue group here, and then I'll also put my green group right here. Okay, and so you can see the first thing basically that's randomly assigned, right? So the idea is I chose it, but like it's random essentially, right? And what's gonna happen here is like, okay, everything that's close to this red point will be assigned to red. So you can see all the things that are close to red will be assigned to red. All things that are close to green will be assigned to green, and all things that are close to blue are blue. And you can see it does a pretty good job so far, like just by pure chance, is that blue's identified just these guys. Red's identified all of one set, but you can see they also grab some of the stuff that's shared with green. So now what we're going to do is like, all right, we identified the points. Now we're going to optimize by moving our cluster, our center. I'm sorry, first we assign. So we didn't assign that yet. So these are all my red points, my green points, my blue points. Now we're going to update the centroids, right? Update those centers and say, all right, move it closer to minimize the distance to these red points. So this red one will move to minimize the distance from the rest of these red points. It ignores everything else. So you can imagine right here, it's probably going to be closer to like right around here. So it's minimizing that distance. This green one's going to zoom up all the way up here, right? Because the only points that are close to it are the only green points are right here. So it's going to get like in the center of these guys. And this blue is probably going to get in the center of this. Okay, so let's see. And you see, that's about right. So you see all the green points now that's centered in there. The red points, now it's in between these two kind of segments that I identified, and the blue points are out here. So blue points pretty much all set. You can tell like there's nothing going to be changed. But obviously now after we update it, we can see, well, green's clearly this is closer to green. So we'll reassign the points. And you can see here, oh, all my green points, and then we have all my red points plus this little one right here. But you can see, because we want to minimize the total distance, we'll actually update the centroid. So this guy will move closer to this big group of points. And you can see this guy right here is going to be left in the dust because it's going to move closer. This red point's going to move over here and identify those. Okay, and then you can see the green's probably going to move closer to the center. Blue probably won't shift, maybe a little bit. Okay, and you can see, there we go. So now we have a new updated center, right? It's like, okay, cool. So now we have the centers here are pretty like, I would say like human level, but like, yeah, that looks about right. But this red point's not assigned yet. So we have to reassign the points. So that's all good. And now if we were to update the centroids again, there's nothing to update really. Maybe it moves a little bit. You can see like the red one moved just slightly because there was a red point still there. So it's kind of moved over, and then I'll reassign the points, which there's no reassignment. I can update and reassigning and nothing will change now. So this is the idea of what K-means does. Now I'll just put random mixture and then I'll do it really quickly. So let's do a uniform point. So this is all random. So you can see the problem is that if I say it's 3 groups, and I just keep going, you can see it doesn't really like technically like, oh, I guess there's 3 groups, but there's not like a clear reasoning for this. And it turns out, let's see if I can restart this. And let's do another random, no, uniform points. And I'm going to add 3 centroids. And you can see these are just randomly placed, right? And this is probably not the best example, but what I wanted to kind of show you is that you can see that classification isn't, what's it called? Like, isn't the same as before. And this wasn't the same data set, but the point I was trying to get at is that it depends on where you put your centers. If you put your centroids in different spots, you might get different results depending on like where those centers basically were initiated. So it's very sensitive to initial conditions, which means like, well, let me ask you guys, if you were to try to fix this issue, what would you do to alleviate the fact that if you initiate your points randomly, like your centroids randomly, and they might be sensitive to initial conditions, what can you do to kind of like fix that? Some options.
I don't, what are you asking exactly? Like how to start it better, or?
Yeah, like you could either start it better, or there's another thing that usually you'll hear a lot of just doing computer programming. So I have the same data set and I put my points randomly, or put my points randomly in some way, and it's going to like find the groups overall. But if I repeat the same process with the same data point, but new centroids like in different spots, I would get a different clustering group. So what are some ways we could kind of alleviate that issue? Because obviously it shouldn't matter where I put the centroids initial. The data is the data, right? So I should be able to find those clusters. So I think Stephen, one thing you were kind of playing with, and this is what most people think too, is you can maybe smartly put in like intelligently put in the points instead of randomly. That's a possibility, right? But then also think of like, how would you determine that? That might be kind of difficult. Essentially, you'd have to know what the groupings are already. So that might be kind of difficult. You might be able to figure out some quick way to like maybe make it a little bit better. But in that same way, if you didn't have that initial metric, whatever it is, you didn't have it perfect, because if you had it perfectly, obviously you wouldn't use the clustering anymore. Problem is like, it's kind of like a back and forth. So one way we kind of do this in computer science, and you hear this again and again, is if you can't do it right the first time and it's going to be different every time, just do it a bunch of times. So the idea there is that basically you would repeat the process over and over again, just to kind of like make sure you're getting the same clusters, and maybe you'd like average over it and stuff like this. So it's kind of similar to like ADA boosting and stuff like, or not ADA boosting, but like boosting and bagging. I guess more closely to bagging. But anyway, the point is that you could like do this multiple times over and over again to make sure you're getting the same clusters. And after so many iterations, maybe you're like, oh, okay, cool, and move on. Obviously that you pay with that with computation time, but at least then you actually have a better idea. It's like, well, okay, either the clusters, if you get different ones every time, like, well, the clusters are not really there, like it's random, or that maybe I have the wrong number of K, for example, all that stuff. So that's the idea for K-means. And what I'll show you, I'll say randomly, I wanted to show you like the density bars. Oh, no, that's not what I want, sorry. Randomly, was it pack circles? Yeah. Okay, so you can kind of see here is that there's some groups in here. And basically K-means is not always the best on this kind of stuff. It does all right, but you can see like it goes a lot slower sometimes. The worst it probably does, I thought I had an example, but I thought it was in here, but I guess not. One is this guy right here. K-means really, really sucks at those crescents that are overlapping. And that's because it likes to try to find like more circular, like oval, for 3-dimensional, right? They look for like this like spherical, hypersphere clusterings. And so it's really bad at finding like these elongated rings or lines, for example, because it wants to find a nice oval or like oval or an ellipse in this case, right? So an ellipse in this case of like trying to figure out, like, I want to group them all together like this. And it just turns out that like these kind of data sets don't do very well with K-means. Okay, cool. All right, so going back to here, let's see here. So that was kind of my issues, right? So I'll talk about this in a second, but one way to evaluate is like, for example, I said how many K do you need? One way you can do this is basically through an elbow plot. The curriculum shows a few different ways you can do it. For example, figuring out a score. There's certain ways you can score basically your system and essentially say, oh, how good are you? This is an example that I think makes intuitive sense, is the sum of square distances. And so the idea here is that basically you want to minimize, basically you want all the points as close as possible to the centroid. So if you only use like kind of going from, let's say, Gaussian mixture, and I only put like 1 point here, let's put 2, and you can go from here. Well, clearly this is not going to like there's going to be overall a bigger distance, but if I had another centroid, we'd actually get a much smaller, right? The overall distance for each centroid will be much smaller. So basically this right here, say, okay, well, with not enough centroids, that distance is going to be pretty big. And then as we get more and more centroids, so you can imagine if I added like, you know, like this many, well, clearly, might take a while, but like you can see like, okay, this is going to minimize the distance a lot, right? Clearly, like everything's going to be really close together, but obviously this is not what we intended. It probably doesn't make sense to have each of these groups split into 3 parts. It makes sense to have these as 3 clusters. So this is why we use an elbow plot to basically say, oops, I keep clicking the wrong one. Basically say, okay, we want it right before it gets to that really small point and basically diminishing returns. So this is kind of like, you're trying to find that, not that inflection point, but basically like right when the curve kind of changes. So usually it's like, okay, like this would probably be about like 6 or, I'm not 6, about like 4, maybe 3 even, depending on how it goes through. So that's how you would use an elbow plot, for example, to figure out what to do. But essentially, you repeat the algorithm with just many different Ks. You start with K1, you know, K equals 1, K equals 2, K equals 3, all the way through, and just see what works out well. Cool. All right, any questions about implementation, how this works? Mm-hmm.
So the
So
the general, oh, sorry.
You can go ahead, sorry.
So the general like process is kind of start at K1, do like K through 10, and then once you get your answer, kind of repeat the process like 2 or 3 times just so you have an understanding of like.
Yeah, like that's usually the best process, I think. It's like you first probably say like, what about how many K do I need? You know, and so what I do, for example, I'll usually say, well, I usually know from what the data set likely is and say, well, how many groups are there likely? Are there likely to be 1,000 groups? Are there likely to be like 1,000 groups? Actually a lot, but like, you know, are there like, how many groups are there going to be? Like, it's like, okay, like, well, it's probably going to be about 5. I was closer to the order of like 20 or like 30 kind of deal. And then you say, okay, let me go ahead and like, I usually don't go like, if it was like 30, I wouldn't go like 31, 32, 33. I'd probably be like, oh, 30, you know, 25, 35, and kind of like do more of like a logarithmic where like there's a lot centered around like where I think the number of groups are, and then I'll kind of spread out just to make sure. So I'll like do like, oh, like 30, 32, 34, and then it'll be like 28, 26. And then as I get further out, it's like, oh, 20, you know, maybe 15, then 10, and then 5. So I kind of like a little more spread out on the edges because I don't expect it to be that far, but I test them out anyway just to double check. And then that way I can generally still see that pattern. There just will be some gaps in between. And then the parts where like, for example, I want to figure out like if I just went from here to here to here, like it wouldn't be clear exactly where this elbow occurs. So I'd add like a little extra points to check this out. But obviously that takes more time because you have to run the algorithm over and over again. And then once you have that, you also might want to say, okay, let me go ahead and try out like maybe K equals 4, K equals 5, K equals 3, and repeat that multiple times with random initiation. That way I can make sure that it's predicting the right way. So that's kind of like the methodology I would do. And this goes close to like when you do a pipeline, when you want to do like multiple parts, where you're like, okay, let me go ahead and try to test multiple things versus like me every time waiting for the algorithm to run and then do the next part and then look at it and then do the next part. I might have more of a systematic way of doing it. Okay, cool. All right. So, and Stephen, you had a question. Did I answer your question, Hassan?
Yeah, perfect. Thank you.
Okay, no problem. And then Stephen, you had a question.
You might go over it, so I'll wait just a moment.
Okay, all right. So going into issues a little bit, which I kind of skipped over. So like I mentioned, initial parameters matter. It's a hill climbing algorithm. Basically, it's a greedy algorithm. And so it does whatever is best in that moment. And so it doesn't look ahead of an extra step. So sometimes like the way I kind of think about this is that you don't just like, like a hill climbing algorithm would be like, oh, you need calories to survive, but also too many calories would kill you, right? So if you're hungry, you just eat a bunch of food. It's like, well, clearly that's not like the right thing. You have to like figure out, it's like, well, in the future, like I want to make sure I don't eat too much, even though I'm hungry right now, you know, something like that. That's kind of like what hill climbing really is in a greedy algorithm, is that, and that's why initial parameters really matter, is that if you initiate in a different way, it can get some really weird results, that not weird results, but like unintuitive results, or at least results that you didn't want it to do. And clusters are not always what we expect. So this is something kind of similar to hill climbing, but the local minimum. So I think I mentioned this before when we did like gradient descent, is that if we have like this general function and we're trying to find the minimum, right? Well, if I put the ball right here and say, okay, find the local minimum. Well, this is uphill and this is downhill, so it's gonna go downhill and it's gonna find this and say, oh, that's the minimum. But clearly if it went the other direction, if it just went over that hill just slightly, it would have found an even better minimum down here. And that's really why the hill climbing. And this is why I say like one of the best kind of like solutions to this is just essentially try different points randomly, right? And basically say, okay, what was the actual minimum or what worked out the best? Okay, and that's how you would kind of do this part too. Sometimes I can't remember if scikit-learn might actually have this built into it. For parts of it, I'm not actually quite sure, but know that you would repeat this multiple times basically and alleviate this initial issue. Because usually it's like, it's rare. It's hopefully harder to get a local minimum than a global minimum. But of course, that's not always true. Sometimes it's just tough to find that global minimum, right? So here's a couple of examples I have. So imagine like there's a bunch of points right here, but I just put 1 point each one. And I want to put like two, what's it called? 2 different clusters or 2 different centroids on here. Or I'm sorry, not 2, 3 different centroids. And so one of the issues with this, like, well, okay, like for the most part, if I put like them randomly, it probably figured out what the K-means, that this is a cluster, this is a cluster, this is a cluster. But you can also have things where it's kind of weird where you're like, oh, can you have like one cluster that is very like these 2 represented by one cluster, and this actually, if I had like multiple points, so let's say I have like 3 points like this. Okay, can I say that this group right here is actually 2 clusters, and this is like 1 cluster? You say, well, that doesn't really make sense. Like at least from like you visually probably say it makes more sense for this to be a cluster, this to be a cluster, this is a cluster, especially when you say, oh, k equals 3. But the problem is if I could come up with a situation like this, where I have the cluster or the centroid initializing right here, and maybe the centroid initializing here, initializing here. Well, the problem is now is that by hill climbing, it says, oh, I'm minimized over here. And it says, oh, okay, this point over here is mine, and this point over here is mine. And I don't know if it kept that in. But basically, it wouldn't have a way to say, oh, no, wait, go ahead and try out, you know, this should be 2 different clusters. And the only way to do this basically is initialize at a different time, right? So you can kind of see like initialization of the centroid really matters. I wanted to just give you guys a couple examples. And then this one right here, similar. If I had, for example, let's say 2, what did I say exactly on this one? I'm trying to remember what the example I had. Oh, I could have it so, no, shoot, guys. Oh, let's say I have 3 clusters again, right? And you might have something where it allows you to go like 3 clusters, like, well, it's not clear, but you can have something like this, where these would get grouped together and this might get grouped together. I feel this is wrong. I feel like I messed up on something, guys. But basically, I'm trying to remember what it was that I had drawn out here, because I think it was 3 clusters, but now I want to say it's 2. The point is that like if I had a lot of points right here, I could cluster these together. But if I had it up here, like let's say these are really far apart in this way, it might actually, depending on things, it might have a nice balance where it might try to find this local minimum, or the global minimum would have made more sense where it's closer to these actual clusters that occur. So I can't remember what I did on this one. Oops, I should have written my answer in there somewhere so I could have checked it, but I can't remember what I was going to ask. But okay, and Stephen, you said you might have a question, or I don't know if I went over it. No, okay. And again, one thing I want to mention is that like K-means, because it relies on the centers, it looks for circular data. So that's why things like this doesn't work really well, because it can't figure out like what centers within centers. All right.